European XFEL, an international research facility and X-ray laser located in Schönefeld, near Hamburg. Researchers from all over the world visit us to do experiments. We all remember how the COVID pandemic interrupted our lives.
As scientists, we are trying to better understand the biological processes behind the disease.
The experiments we did here during the pandemic were a great example of the scientific community coming together. We had researchers from the UK and Germany working with us to understand how the proteins in the SARS-CoV-2 virus work.
And to better explain this to you,
Our colleague Raphael has developed quite an interesting button.
Yes, this will help you to get a better understanding. Okay, that's crazy.
let's go.
The biological samples we look at here at the European XFEL can come from anything, like animals, plants, bacteria, and so on. All living organisms, as well as viruses, are made up of very small parts which are mostly proteins and DNA. And the shape and structure of these biomolecules are crucial for their function.
Molecules are made of atoms and form structures such as DNA and proteins. The structure is important for understanding the function of these molecules. We use the X-ray laser to reveal these structures. In the case of the coronavirus, we are looking at two very important proteins, MPRO and PLPRO. These are crucial for the replication of the virus. If we understand the structure of these two proteins, we can look for approaches and drugs to prevent the virus from replicating and thus combat the disease.
Und die Krankheit zu bekämpfen.
But to look at these small shapes, to see their exact structure and how its atoms are organized, we need something special.
Because visible light does not have a short enough wavelength to see these tiny nanostructures directly. First, we need an almost 2 kilometer long particle accelerator. It boosts the electrons to almost the speed of light, and more importantly, pumps them up with energy.
At the end, we send them through a magnetic slalom course. Here, they give off laser-like flashes of X-ray radiation, which then, et voilà, is our high-energy femtosecond X-ray laser with up to 27,000 pulses per second, which we use to read the structure of molecules.
When the virus enters the human body, it binds to the cell surface and is taken up by it. The virus then releases its genetic material into the cell and uses the cell's internal machinery to translate it into an amino acid chain. The two proteins we're looking at here, PLPRO and MPRO, are responsible for cutting the amino acid chain into functional pieces that then fold and form proteins. The virus needs these proteins to make more virus parts and replicate itself. Here, we are trying to understand the function of PLPRO and MPRO so that we can find inhibitors to break the life cycle. To study these proteins with the X-ray laser, we first have to produce them in large quantities using bacterial cultures. Then, the proteins are isolated from the bacteria and purified in this machine. It is not easy to get the proteins to form crystals. That's why we have to try out a lot of different conditions. This robot helps us to find the right conditions so that the proteins arrange themselves in crystal lattices.
Because in crystals, the proteins are ordered in lines and stacks, a bit like eggs in a box. This ordered structure gives a better signal when placed in the X-ray beam, so that we can measure better images when we place the sample at the interaction point.
The protein crystals that we just produced with the robot in their crystallization solution are put into these sample vials and then taken directly down to the experiment in the experimental hall.
Here, we can prepare our sample and directly deliver it into our experimental chamber as a liquid jet containing our crystals. And now, the magic happens.
The ultra-short X-ray laser pulses of the European XFEL travel through the beam pipe into the vacuum chamber, where they hit the sample, which consists of crystals of molecules in a liquid jet. The structure of these molecules in the sample leads to a characteristic diffraction pattern, which is recorded by the detector. Due to the different orientations of the crystals in the X-ray beam, each diffraction pattern looks different. Researchers record thousands of diffraction images and process them in the data center using complex algorithms. This reveals the three-dimensional structure of molecules in the crystals and allows them to make time-lapse films of biological reactions.
All the data that we can collect here at our instrument during our experiment will lead to the image you have here, which is the electron density map, which will show us where every atom in the molecule is located.
But that's just the start. In order to understand how to make drugs to block the action of these proteins, biochemists need to see the process as it happens, not just a before and after shot.
Which is why we need such extremely short, high-frequency X-ray pulses. This is like having a short exposure time on the camera when you film someone running. If the exposure would be too long, it would be blurry. We use these very, very short pulses to take sharp pictures, which we then put together for a stop-motion animation. We call these molecular movies. Using them, we can literally see how a protein or an enzyme is reacting in real time.
Hey. Okay. On three? One, two, three. This research can be applied to design new medicines based on the structure of proteins which cause disease. The discoveries we make here can be used as the foundation stone for drug design by scientists and pharma companies all around the world.
Auf Wiedersehen.
See you at European XFEL.